explanatory tutorial looking at the functionality of MyGeoTwin version 09.05.2021. MyGeoTwin will be explained with real data to provide context to each tool embedded in the software. Just to recap, the purpose of MyGeoTwin is the visualization and analysis of geophysical imaging data in the form of point clouds and as a single point of truth for all data related to the ground for a project. This includes visualization, aggregation, analysis, auditing, and sharing of all data related to the project ground. When MyGeoTwin is first opened, add your username and password. Then select an appropriate server or an alternate in the event that one is down. If you're on fast internet, agree to accept photos and then click Load. Each project is password protected and each user will only have access to specified projects. So select your project and load. To start, we will open a model of Doha Port to look at how to move around windows and how height datums are handled in the software. The port and approaches were surveyed in just 4 days. Once loaded, 2 windows open, the main window and the 3D tab. Down the bottom of the main window there is an info tab where basic project data and notes are recorded. To the right is a help tab. Here basic reminders about how to use and move around the software are provided. To begin with, adjust the window to suit your screen resolution. Once comfortable, start to move around in the model space. It is best to use a mouse. The wheel will zoom in, the left button to rotate, and the right button to pan. Some functionality is available on the keyboard with the left key and the right key and the up and down buttons. Also, you can use the I and the O buttons to zoom in and out. To look at how height datums are handled in the software, we will draw a cross line in the approach channel. Click Draw, then left mouse to start the line, left click to add a second node, and right click to end the line. Using the mouse, rotate the model to a side view, and we can see that the model is currently relative to a project datum, usually lowest astronomical tide for a port. By moving over to the menu, we can check relative to ground, and all data is automatically adjusted to hang off a common zero datum. All of the newer projects have this functionality. Changing the height datum relative to ground can be a really good way to view the geology across a site. Use the left and right mouse buttons to pan through the model. Then use a horizontal slider to push a horizontal section through at -3.5 meters below the datum. The depth indicator has just turned red, indicating that data is loading. Once loaded, we can see the caprock or calcarenite at the channel entrance, silts and sands at the bend, and some isolated caprocks in the channel, and caprock in the harbour. Now, looking at Nome in Alaska to understand base maps and line files, we built this model from open source data to help a client better visualize placer gold deposits and associated mining risks. In all, some 3,500 boreholes were mapped, along with the gold concentration in each sample. A base map is any georectified horizontally oriented image set at a specific height. Contoured images can be brought in as a surface elsewhere. This model has 3 base maps: the air photo, a geology map, shown here, and a side scan sonar image. There are also 3 line files. Line files can either be 2 or 3-dimensional and represent maps or infrastructure. Here, line files are mapped boundaries of geology or mining concessions. Now let's look at the Sydney Harbour Metro crossing. Here, 14 kilometres of data, or about 2 million data points, were collected to 40 metres penetration in 2 nights. We will use this project to understand 3D surfaces and 2D vertical sections. After turning off the 3D surfaces, we can see the tunnels from Barangaroo to McMahon's Point on the right. Now, let's look at seismics. This function is mostly used for visualizing raw seismic data, but can be used to view any 3D vertical sections if the orientation is known. This model contains seismic sections, the consultant's interpreted section, and the processed refraction data. For the first time, anyone can easily see raw seismic data and try to make sense of it. These analog seismic sections are all individually hand-processed. This is a major difference with advanced digital imaging. Advanced digital geophysics is machine-processed in just a few hours. And here we have analog data where the geologist has had to hand-draw what they think are the relevant geological units and then relate them spatially to neighbouring sections that might be tens or hundreds of metres away. Here we have 3 sediment structures and rock interpreted across the site and then surfaced independently. As mentioned, the consultant's section is digitized by us as well as refraction, and it all can be now visualized in real space. So now we can move finally from isolated interpretations produced by normally unchecked experts delivered on a piece of paper to seeing how they look in real space. Any section on a piece of paper can be put into the Geology Digital Twin if the alignment is known. In the case of analog seismic data, here positioning data was stripped off the SegWi files where provided. In the case of seismic sections alone, we can now see how processed data has included data acquired through very sharp turns that should normally have been clipped and discarded. Looking now at 3D surfaces, it is possible to scroll through the layers in the main window. It is also possible to see the layers in the 3D window. Simply hit the List button to open the list of included layers. The Show button above turns on all the layers if they are not already on. The transparency of each layer can be adjusted and turned off individually. For this exercise, let's have a look at the interpreted seismic rock surface. When you are happy with the layers, simply hit Hide the List. Now that we have the interpreted rock surface and the raw seismic interpretations in the one visualization package, for the first time we can check or verify that both datasets are correctly processed. Zooming in, we can already see multiple instances of large busts between gridded surfaces and the interpreted rock from the seismic sections. Additional errors are present and will be reviewed in a separate and upcoming video on the Metro. In some cases, datasets are very large and cover multiple work areas. In this circumstance, the dataset may be broken up into multiple models. To examine this, we will look at the Geelong Harbour. In this case, 550 line kilometres or 14.5 million data points were collected in just 8 days. The data was broken up into discrete areas. We have the inner harbour area, the middle harbour and the outer harbour, primary dredge spoil area and the secondary dredge spoil area. To move between the models, simply check Select 3D Model. Move to the map and click anywhere in the model you wish to open. In this case, the inner harbour area. Again, moving to the outer channel, the same process is followed. A geology digital twin was also made for the Eden Port development. Approximately 14 line kilometres or 1.2 million data points to 12 metre penetration were collected in just a day. Using this model, we will import the Advanced Geophysical Point Cloud, import and work with construction alignment as a DXF, create and work with vertical and horizontal sections, measure and use the settings, and get familiar with boreholes. It is possible to view the Advanced Geophysics Point Cloud. This will be stored on a user's computer if made available and loaded through the main menu. Once loaded, simply activate the PTS button near the bottom. By zooming in and rotating around the data, the basic geological structures can already be seen. Diving into the data, we can see the sheer number of points and data density. There is a point every 5 metres in the horizontal and 25 centimetres in the vertical. Now, let's look at interrogating the data. Firstly, it is possible to bring in a construction alignment as a DXF file. Just make sure it is correctly positioned and in the project datum exploded. In this case, this alignment is one of the proposed wave attenuator options. Once imported, a vertical section will be generated automatically. Already it is, from the point cloud, we can see that one of the piles is very close to the vertical geology. To confirm this, we can open and request a horizontal slice at minus 15.5 meters below datum. Indeed, the pile will be too close to the geology drop-off to be safely installed. Fortunately, it is possible to edit the construction alignment here. Simply click Edit Profile button, hover over the node so it turns red, and left-click to move it a little away from the edge. Then create a copy of the alignment and save it. We can also draw vertical sections anywhere in the data box. Hit Draw, left click, left click, left click, and right click to end. This is a multifaceted line, and we can also draw single faceted lines. Again, draw, left click, right click to end. The vertical sections are live entities. Color gives an indication of the GeoTwin value, but exact values can be seen by checking the Show Value button at the bottom of the window and pointing anywhere at the section. Values are reported above the 3D window. Colors or isolines can also be adjusted as required. To add an isoline, simply add the value in the box provided and hit Enter. In this case, 2.25 GeoTwin units have been added. The Colors button allows the color curve to be adjusted to emphasize low or high values as required. Once happy, check Update. The Save View button will save this session, including any changes to the colors, to your hard drive. The save session parameters can be loaded next time you use the model or shared amongst team members. MyGeoTwin has a measuring tool. It works like Google Earth or any other measuring tool. Press Measure, then left-click to start and left-click to end. Values are reported above the 3D window as normal. To reset the tool, click the Measure button twice. The color of the line can be changed simply by clicking on the color box next to the Measure button. Measurements can be made on horizontal or vertical sections. For example, we can measure the distance from the wave attenuator node to the vertical geology. Here, it is 13.27 meters. We also have a center screen option. So if you get lost, simply push the center button. The user can also set a maximum penetration for the dataset here. Simply check the maximum penetration button and set the depth to the desired value. For example, 6 meters below the ground. Now each subsequent vertical and horizontal section drawn will report the value to this depth. The vertical exaggeration can be changed to suit the user preference. The default for this project is 5, but it can be changed. It can be increased or decreased as required. In this instance, we've reduced it to 1. We can also add a reference level at any height relative to the project datum. For example, minus 16 meters below the datum. Now a line will appear on each open vertical section. and every other subsequent section generated. There is also an option to laterally shift vertical sections through the model. The default for this projection is 5 meters. So left-click on any section to activate it, and then use the L or the R keys to move the section toward or away from you by 5 meters. The thumb buttons on a gaming mouse will also work, if they're available. The distance moved in each step can be increased or decreased as required. So if we change it to 50 meters, we can see this occurring now. Moving to boreholes, these are largely controlled via the boring box on the main menu. All data can be stored on the server, however it may be more convenient to store larger PDF files on the user's computer to improve speeds. Specific instructions will be provided on a case-by-case basis if this option is used. Downhole data such as SPT or anomaly data may be available. SPT data is in blow counts and bracketed in units of 5 N counts. Anomaly data would normally be just on-site observations and unitless. Anomaly data is reported on the bar above the model as shown. The diameter of boreholes can be adjusted from the default to suit the user preferences. Geological units can be moved in the legend bar to aid user understanding, as well, and colours may be changed. Again though, changes in the legend and colours will be lost if the session is closed, and you will need to save a view to keep a copy of these changes. Vertical and horizontal sections can be hidden or turned on as required. Same with 3D structures. We can also turn off boreholes or hide downhole information such as SPT and anomaly data. Boreholes are live elements within MyGeoTwin. When the user points at a borehole, the name, position, start height and geology will be shown at the cursor above the 3D window. In this case, borehole 11 is at the cursor. We can also look at borehole 4 with loose sands above the shale and then rhyolite. Now, because this is a reasonably complete geology digital twin of the Eden Port, we can start to verify boreholes. The first basic check is of the heights. To do this, simply turn on the bathy and turn off everything else. Immediately, we can see that borehole 7 stands above the bathymetry. To examine this borehole in a little more detail, turn on vertical sections. Then click Draw, and left-click to start, left-click to end, and right-click to end. Panning and zooming with the mouse keys, we can already see the seabed and the rock surface are about the same distance above the seabed and the rock depth reported in the advanced geophysical data. Given that most geotechnical companies do not have a surveyor in the field, positioning and height errors are very common, As already mentioned, MyGeoTwin is an excellent auditing tool for ground data. These checks are very difficult and not so intuitive to make outside of this environment. Now, we can clean up this window a little bit by removing unwanted sections. To do this, simply left-click on the unwanted section, check Overwrite, hit Draw, and repeat this for other sections that need to be removed. Now, looking at the construction alignment, there is always a temptation to link boreholes and move that as a surface to CAD for design purposes. Indeed, we do have this functionality as well. Once you have your view right, simply click on File Name, create a new file. We'll just call this Surface for now. And I'll just turn off base maps. To get the alignment right. And then left click at the correct height on the first borehole. After clicking Digitize. And we can see that the line has started. Then move to the second borehole and left click, and the third borehole and left click, and then right click to end. Now we can see that the boreholes are linked at the top of the rock and the construction alignment. To be honest, we more just made this tool to show you why it should not be used more than for practical use. To illustrate why, as we are in a geology digital twin, let's look at the digitized alignment in the context of the advanced digital geophysics. Left click, and right click to end. And then we'll rotate back to a side view. Firstly, we can see that the boreholes in the advanced geophysics align perfectly at the point locations of the boreholes. The vertical feature between the red rock and the structures is visualized correctly. Let's just turn the base map back on for context, and immediately we can see that the straight line between the boreholes badly misreports the rock heights between the boreholes. Misreporting of the rock heights is a major reason for construction failure. Now looking in the horizontal, we can see the complex vertical feature from a different angle. Accurately targeting boreholes and then reporting verified complexity to engineers is crucial for sustainable design and managing risk for construction contractors. Engineers can now either avoid this area or warn construction contractors during the tender phase. We can also inspect the outdated analog geophysical interpretation by turning on available sections and closing unwanted ones. Using L or R on the keyboard, we can push the advanced geophysics section back to see the analog geophysical section behind. The rock level seen in this section is darker brown and does not reflect reality in any way. It misses the vertical complexity entirely and then is dipping away to the right instead of rising. So the data from outdated analog acquisition methods similar to Metro is useless and must be thrown out. We can also turn on and off the advanced geophysics section above as well. Positioning errors are quite common and quite difficult to detect in PDF borehole reports. As such, an error can be queried quite late into the design and even construction phases. Here we examine a land site for a transmission tower. Data was collected over 2 days and processed on the fly. In this case, we have 2 borehole campaigns undertaken several years apart by 2 different contractors. Adding transparency, we can see that one is at the correct project height, but the other, provided as a certified error-free report, is at the wrong height. This height error was detected as soon as the model was first opened and the contractor required to correct their data. The new model was then created with a corrected data, and the boreholes now align. This area also highlights another common issue with boreholes. Boreholes, particularly in sediments, are a very coarse sampling technique. They certainly do not produce a facsimile of the ground. As seen in Eden, they often miss key layers if they are not targeted. If we take a cross-section through some of the data, we can see a red layer at the top corresponding to dry wind-blown sands. A deep blue layer and then a yellow-green layer below. Except for a slight dip in SPT values, the blue layer is almost identical to the lower layer, and would have been very difficult to detect in the field unless the contractor knew to look for it. This blue layer represents a salt deposit deposited by groundwater movements, but this layer is key to safely earthing the proposed transmission tower, so is critical knowledge to the owner. This example highlights beautifully the importance of always getting advanced digital geophysics first and targeting boreholes both vertically and horizontally. Moving to seal rocks, we will again see the importance of targeting boreholes as well as see how site photos are handled in MyGeoTwin. Here, the client wanted to make sure of the reasons for a road slip before repairs were attempted. Firstly, we can hover over the hourglass to open photos of the site and see the extent of the slip. The arrows will give an indication of the direction of the photo. The photos, when available, can be enlarged with a right mouse button and moved with the left mouse button. Double-clicking the photo will close it. The advanced geophysics in this case is brought into the model via a cross-section function. Then turning the topography on and adding a little transparency for context, we can examine the data in situ. Here, there is a deep blue section. This represents water along the slip plane that is the reason for the slip. It is very unlikely that the borehole would have detected this layer. However, in this case, the geotechnical team subsequently confirmed the layer. So based on this information, repair strategies were developed, as well as mitigation strategies for managing the slip plane further down the hill. Lastly, in borehole management using MyGeoTwin, we will look at how geochemical data is handled. To do this, we will examine a model we created for a client to consolidate existing data to help them understand knowledge gaps and plan data acquisition and risk management strategies at project initiation. Setting up a geology digital twin is an excellent way to develop acquisition strategies, create a digital workflow, and instantly audit all aspects of incoming data. After adjusting the screen and zooming into an appropriate level, we can add a little transparency to the bathymetry. Now, if we turn on the geochemistry and click in the box that appears above, we can scroll through the chemical tests available with the mouse wheel or select tests from the drop-down. Here we have iron, copper, zinc, lead, oil and phosphorus. Pointing at any of the bars next to the borehole will provide depth and levels above the 3D window. This is a very good way to feed all stakeholders environmental and engineering data in the one model to ensure sustainable design and effective construction strategies that adequately communicate contaminated soils risks. In our last example, we looked at the Rio Magdalena in Colombia and demonstrate the export functionality. Here, the rivers are key for transporting goods efficiently between towns where roads may not exist or are frequently impassable. To assist in creating a long-term management plan and dredge strategy, we mapped over 300 kilometres of river. Just turning off bathymetry and putting in a horizontal section. And now we can add 2 verticals, a multi-faced one, and a simple line. Now, to export KMZ, simply click the KMZ button, select a destination folder, give it a name, and save. To export a DXF, it's a similar process. And the GINT button exports borehole and downhole data in the basic GINT format. Looking at the destination folder then, we can see borehole data is exported to point or survey folder, lithology, and downhole if available. These are all text files that can be opened in any text editor or visualization package. The point file contains point ID, positioning data, heights, length, azimuth, and dip. The lithology folder contains point ID, from to depths, UCS data, and a basic description, and downhole data, if available, will be similarly ordered. The KMZ data is a bundled Google Earth file that opens directly into Google Earth or a similar program like Cesium or ArcGIS Earth. This is a very good way to provide stakeholders with complex data in a simple format that they will be able to use. We can move around the map just like any other Google Earth image. And turn on and off different layers as needed. Boreholes are also exported and contain basic downhole information in the point. The DXF export will deliver vertical and horizontal sections as surfaces. In addition to the DXF, a PNG of the horizontal section is exported together with a companion world file that contains the positioning data for this file. In addition, a picture of the data for each face is exported separately. It is then a matter of applying a texture to each horizontal and vertical face in CAD. This has been a video on the functionality of MyGeoTwin. MyGeoTwin currently represents the best tool for visualization, aggregation, analysis, auditing, and sharing of all ground asset data for the life of that project and beyond. Look out for more of our videos, including shorts on specific functionality and project examples.